All right. Hello, everyone, and thank you for joining us today. My name is Matt Willard, and I'm the marketing director at Yokogawa Fluence Analytics. We're thrilled you all have decided to attend the Monitoring and Analyzing the Stability of Biologic Medicines webinar. Today's panelist is a world-renowned expert in macromolecular characterization, Professor Wayne Reed. Dr. Reed is a professor of physics at Tulane University in New Orleans, Louisiana, and he is the inventor of our ACOMP and Argent technologies here at Yokogawa Fluence Analytics. This presentation was completed with work also performed by Dr. Curt Jarand, who's also a researcher at Tulane University. Argent, which helps teams accelerate biotherapeutic formulation development efforts, is a light scattering platform that provides real-time stability monitoring across 8 experiments simultaneously. Argent can detect the onset of aggregation and other molecular changes due to thermal, chemical, and mechanical stress. Visit our website at fluenceanalytics.com to learn more. Please feel free to use the chat or Q&A feature throughout the webinar if you have questions. Professor Reed, thank you for agreeing to participate in today's webinars. Your talks are always filled with useful information that help biopharma teams problem solve in a better, more efficient manner. I'm ready to jump into this webinar, so at this moment, I'll hand it off to you. Take it away, Professor Reed.
Okay, thanks for the introduction, Matt. All right. Well, we have some interesting results here to show today. You already seen the title, and I'd like to show some of our current and recent sponsors. I'm sure you recognize a lot of those names. There's also support from Tulane University itself. So I will get into, here we go. We're going to focus on dynamics, kinetics, and stability of biologic drugs. So you all know more about biologics than I do, but the types of biologics we're working with are monoclonal antibodies. These are some of the disease conditions they address. Like an old-fashioned mouse here. Okay, mRNA vaccines, which were catapulted into the public eye during COVID. Viral capsids, which are one in an array of delivery vehicles in gene therapy. Protein polysaccharide conjugate vaccines are really an ingenious approach to vaccines. And then there are other biologics, but we'll show some of these as we go along. What I want to do now is look at two different phases of biologics. One is when they're in equilibrium. You have them in a formulation, they're shelf stable for months on end, maybe even a year or more, and they have stable characteristics like their molecular weight, radius of gyration. You know what these things are. Variable coefficients. We usually call them A2. In pharma, they're often called B22, and so on. It could also include, circular dichroism spectra, et cetera. The point is they're stable, not changing in time. However, there we go. Oh, God. There are plenty of non-equilibrium processes which are not stable. One of the worst ones is colloidal aggregation, a very unwanted phenomenon in any biologic because it reduces the efficiency and sometimes it's even harmful to the patient and certainly won't make it through FDA or other organization. Then there's dimerization, reversible associations that can happen, phase separations. There could be degradation such as hydrolysis or other chemical reactions. So that's the non-equilibrium side. So we'll look at a little bit of equilibrium and then go into some non-equilibrium processes. Virtually all the data, I think with one exception in this presentation, was taken with a Argent. So it's, as mentioned, you have simultaneous static light scattering. Each one is individually temperature controllable, has its own stir and its own laser and detection. So they're really independent of each other. So you can map out different conditions and products at the same time. So let's just look a bit here at equilibrium characterization of, this is a monoclonal antibody. This, by the way, was from Biogen. This is published, so it's in the public domain. Without going into a lot of equations, what we're measuring is the light scattering. Okay, this is the intensity. That's the first thing we're doing with what's called SLS, static light scattering. That which we measure here, this Rayleigh scattering ratio, together with the concentration of your biologic, and K is just a constant, related to the mass. It's related to the virial coefficients, A2, A3, and A4. And here we're looking at a biologic that was at 190 mgs per mil. That's 19%. And as you know, this push in the biologic sector to make high concentration formulations so that they can be injected fairly rapidly, as opposed to having a very dilute IV drip and having a patient sit under that for hours. Now, when we look at the scattering curve here on the right, that intensity is a function of concentration. If this were an ideal solution, it would go up linearly, as you see with this line here. But if the biologics are interacting, the molecules themselves interact with each other, then things can happen. In this case, you see it bending down A2. That's due to a positive A2. A positive A2 is generally good because it signifies repulsion and hence not attraction and aggregation or other associations. What you do, you see it come to a maximum here, and that'll happen with just an A2, but the fact that it then comes down after that is where A3 and A4 are coming in. These are perfectly transparent solutions. There's no turbidity at all. These are corporations that have the resources to make extremely pure formulations. Okay, so I don't want to dwell too long on this, but one of the ideas is that in order to anticipate non-equilibrium behavior in biologics, maybe there's some equilibrium properties that already tip you off about that. So if we look at A2, for example, remember that comes out of here. This curve is the one I just showed. This one here is from the National Institute of Standards and Technology. They have a standard monoclonal antibody now. And this one here was also from Biogen, but it was not suitable for formulation, was abandoned. This one here did make it commercially. A2, you can see, is on the order of 10 to the minus fourth for these two stable ones here, whereas that's not 10 to the minus six. So it's well over an order of magnitude less for the unstable one. And what A2 measures is the energy interactions between two particles as they approach each other. If it's positive, it means they're repulsive. If it's negative, you're probably on your way to associations and or irreversible aggregation. But in this case, because these are about the same size, the monoclonal antibodies on the order of 150,000 grams per mole. And yet they have this huge difference in A2. So that's related to the fact that this is, let's say, a stickier kind of a monoclonal antibody. Also, you notice that the stable ones, this and this, have a maximum and then decline. So they have a measurable A3, whereas the other one, there isn't even an A3 measurable. It's just not, the repulsions just aren't strong enough. So I'll leave it there. There's some other features we could look at, but rather move on. So what can lead to instability? So we move away from equilibrium and into the non-equilibrium processes. Lots of things can stress a biologic and make them unstable. There are things that affect all of the molecules in the formulation. We call those global stressors, since they affect all molecules equally, like the pH and the temperature. In fact, see if this will come up. Didn't come there. Okay. For temperature, if you look at this figure over here, now what we're going to be showing a lot of is MW over M0. M0 is the starting molar mass of your, whatever it is, your biologic, in this case, a monoclonal antibody. MW is its value at every moment thereafter. It's a time-dependent function. So when there's no aggregation, it's 1. If you get a value of 2, it means on weight average, you have 2 biologic molecules per aggregate, 10 would be 10, and so on. I had to put this on a log scale because the variation is so great with temperature. These are in seconds. That's 6 days going out to here. And you can see at 30 degrees, this monoclonal antibody was perfectly stable, whereas when you turn it up to 45, it lasted days, but then became unstable. And as you raise the temperature, it rapidly becomes very unstable. By the time you're in the 60s, it's aggregating within tens of seconds. So that's a temperature stressor. Now excipients, those, anything you can think of, the electrolytes, surfactants, chelating agents, sugars, etc. those can also provoke instability. So here's an example of just bovine serum albumin dialyzed against guanidine. I'll show the method we're using to do light scattering under dialysis in a few minutes. But what you see is that it's stable as the guanidine increases, and then at pH 8.5, it suddenly goes unstable. It aggregates massively. So we have a stability regime, and after that, it's totally unstable. If we change the pH, it lasts a lot longer before it goes off. So let's see. Those are our global stressors. Now, if we go to local stressors, these only affect molecules at the point of stress. So, for example, in contact stirring, where you have a magnetic stir bar, let me show, I have a picture here. It'll come up. Oh my God, there we go. Okay, so if you look at the two cuvettes, one has a magnetic stir bar on the bottom, this blue one here. This one has a suspended impeller, which makes no contact with the cuvette itself. And these were stirred with a monoclonal antibody at 500 RPMs for one whole day. And you see that the one that has the non-contact impeller is perfectly flat, it's stable. Whereas the one that had the contact immediately starts to aggregate. So that shear, that stress that's happening right around the stir bar is causing this to go off like this. Other types of mechanical or local stressors, peristaltic pumping. Often thought to be a gentle way of pumping because there's no pistons and hard surfaces. You just have a malleable tube and rollers that express the liquid through it. Going through those rollers actually damages the biologics quite a bit. And so you have to be very careful with that. Any other type of shear can do it. Even filtration, which is kind of ironic, you oftentimes filter to get aggregates out, but it can concentrate the biologics at the filter surface and actually enhance aggregation, the opposite of what's wanted. And there are other materials which it merely comes in steady contact with, whether it's metals or ceramics, plastics, that can also cause instability. Okay, so those are golden local stressors. And you might ask, when you're dealing with something like colloidal aggregation, is that even reproducible? It could be totally stochastic. So what we show here is that with a global stressor, in this case, temperature, we held it at 70 degrees C. This is a monoclonal antibody. We repeated it 16 times. And over here, just BSA at 58 also 16 times. And you see they're very closely clustered, each of these separate repeats of 16 each, showing that it's actually operationally deterministic. It's not random and it's not stochastic when we have this temperature, which is a global stressor. Now, if we go to the local contact stir that we saw with the radical effect it had on aggregation, we can't even fit that data for both of these on here. So if we just look at how BSA reacts to, and this is just fairly gentle, 100 RPM stirring, you can see that it's all over the map. It goes anywhere from very little effect, some but little, this is about an hour and a half, to very rapid aggregation and everything in between. So it's very, very stochastic and unpredictable. Whereas the global one was quite deterministic, operationally deterministic. So I have an old-fashioned mouse. It's acting up. Anyway, we can actually get a quantitative rate, an aggregation rate, AR as we call it. And remember this, we keep showing MW over M0, that's dimensionless. So when you take a time derivative, the units are 1 over seconds. In most of these aggregation and other phenomena will have an initial linear phase, not always, but usually. And if you take the slope of that, you get an aggregation rate. This is about 0.005, which means a 0.5% increase in aggregate weight average mass per second. Okay, so that's a real number we can do stuff with. And here is an example of Arrhenius plots that we made for 4 proteins. If we look at the 4, again, we have the NIST monoclonal antibody, it's a standard. We have the Biogen one, that's a commercial product, the Biogen one, which couldn't be developed further. And this one up here is an academic one. Remember, the higher the aggregation rate, the more unstable. So unfortunately, the academic one stands out as the least stable. Of course, academic labs usually have thousands of dollars and not millions to try to produce their monoclonal antibodies. the point here is look at, the Arrhenius equation, the aggregation rate, chemical rate constant, is proportional to the exponent of whatever the activation energy of the process is divided by kV and T in Kelvin. So we do that here. We plot it versus 1 over T, and the slopes are activation energy divided by Boltzmann's constant. And you can see they're about the same for all three of these, and this one's not much different. So that's not what's regulating the propensity for aggregation. It's something else like, the stickiness, that pretty coefficient here. What's the probability that when they encounter each other randomly, two biologics, that they actually stick rather than bounce off? So anyway, you can see this is quite a few orders. It's like 8 orders of magnitude, all the way from nearly 100 to 10 to the minus 6. Okay, and these breakpoints here correspond to the melting transition regime. Okay, so tying it together, when we have stable biologic formulation versus unstable, what we can do is talk about a trajectory. That trajectory could be a temperature ramp. You're going up, it's stable, and then it goes unstable. It might go up or it might go down. We could be doing this a pH scan, or we might be putting in excipient. And we're basically looking, oh yeah, nice, stable. We see this whole regime is stable. That's good. You can do a formulation there. But then once you hit these regimes, it goes unstable. For example, aggregation. If you stop however you're ramping this up, and just look at it, this one condition, then you get a kinetic. You plot the molecular weight versus time. It's going up for aggregation events. So these are different points on that instability curve. And if it's degrading, they would be going down. Now, I put molecular weight here, but it could be some other characteristic. It could be a hydrodynamic diameter or quantity of alpha helix or whatever else. Okay, so one thing we use as a nice adjunct to the Argen is this cuvette-based approach, where we take a standard 1 centimeter cuvette used in any spectroscopic instrument that takes them, and we modified it. Well, we built this device here, which then has non-contact stir. We saw the importance of that. It's driven by this stepper motor here, and there's a shaft that comes through. And then we have this cylinder here, around which is hermetically sealed the dialysis membrane. And so you have your biologic and fluid one, the blue fluid here, that's sitting inside your spectrometer. In this case, we're using the Argen for virtually all of the data. But you could put it in a UV vis, you could put it in fluorescence or circular dichroism or Raman, whatever will accept the 1 centimeter cell. The dialysate goes through fluid 2, and so it diffuses through the membrane, changes the condition of the biologics in fluid 1, and those you're monitoring with your optical instrument, in this case, the Argen. Now, an important advance we had is we found these ion selective field effect transistors. They're really tiny and fit beautifully into a tiny cuvette. I mean, there's not much real estate in there to get all this stuff in, but it's all in. And that will measure the electrical conductivity, which will be related to the concentration of any charged dialysates, and pH. There's also ones available for oxygen. Okay, now if you get this to work, if you take the membrane away and just leave the impeller, and now you can add, we call this automatic continuous dilution. We can also do automatic continuous mixing, which I won't get into here. But the dilution is simply you have your biologic at a known concentration, choose your diluent, maybe the one that the biologic is in, and you start pumping in at a certain rate, and you withdraw at the same rate. That keeps the volume constant in the cuvette, but it exponentially decreases the concentration of the biologic. So just a few things on that. So it uses the 1 centimeter cuvette, which fits right into the Argen and other devices. You get a continuous record of how biologics will respond to electrolytes or other excipients diffusing in through the dialysis membrane. Again, you can use it in any of these instruments that accept the cell. And sort of weird. Okay, that's the controller for this, and you can see the device, and it's the real picture of it. We first came out with using it on a wide variety of macromolecules. We did polysaccharides, proteins, some synthetic polyelectrolytes, and a couple other things, gelatin. And then with these ions, so this is such a powerful addition to the platform that we published that Measurement Science and Technology just a couple of months ago. So here's an example of using automatic continuous dilution. This is actually taken with the Brookhaven instruments, so we get the dynamic, the diffusion coefficients in addition to the light scattering. This is your typical light scattering representation over here. Okay, so from this, which is what we get from Argin, you get a molecular weight average, A2, and you can get other higher ones if they're there. Again, if it's greater than 0, it's repulsive, that's good. If it's less than 0, then you're probably going to run into problems. With the dynamic light scattering, you get the diffusion coefficient. I won't go into this. You get the hydrodynamic radius. You do also get the what's called KD. It's the first interaction parameter in diffusion, which is helpful for assessing. It doesn't measure viscosity, but it kind of indicates it because it's also a hydrodynamic measurement. So if you're looking to see if your biologic is going to be too viscous at high concentration, this KD can be informative. If it's greater than 1, typically, then you have a greater chance of success of low viscosity at high concentration. If it's too low, it's probably going to get too viscous to ever be able to inject. Okay, so here's now running a continuous sweep in pH. We went from, that's on this side, from 7 down to nearly 3. This was with polyadenine, so it's an RNA homopolymer. And you can see that as we go down, it's fairly stable, and then it starts to aggregate. And that aggregation starts right around 4.9. So we've got that there. The pH, which is stability, then is above 4.9 to 7. We can also go the other way. And then you have a plateau here. At first, you look at that, you say, that's probably just a glitch. But we repeated it like 5 times. It's there. And what it, this thing's really, okay. What it respond, it corresponds to is as you keep adding protons, as you lower the pH, you start to protonate the adenine groups themselves instead of lowering the pH of the solution. That's why you get this plateau. So you see the effect of actually protonating your biologic. Okay. So I'm going to give a very quick case study. We did this with Moderna. It was just published a couple months ago with mRNA association and dimerization autohydrolysis. They provided us with a series of mRNA samples, different lengths. Again, this is all published. And so this is interesting. When we now use the Argen and put dialysis against NaCl, again, MW over M0, the mRNA, you can see the mass, the aggregation is monotonic. It just keeps on increasing as you increase the NaCl, whereas this is guanidine hydrochloride, right here, guanidine, we just call it GD. And you can see initially it's doing the same thing as NaCl because it's also a monovalent salt. So it's doing the same thing, but then all of a sudden it goes through this huge, massive colloidal aggregation, which saturates the instrument. And then if you keep going, it comes down on the other side. So it's like a window. You get this reversible, it's like I said, it is reversible, and we call it an association window. So the idea here is this, by looking at the interplay or how the biologic behaves when interacting with a denaturant, guanidine hydrochloride, and with just a simple electrolyte, we can kind of untangle what the effects are behind the instability. See, and this is very interesting. In this window here, so that's over a certain concentration of guanidine, if we just take in the Argen and put the sample at a fixed value of the guanidine, you can see it follows the window quite well. Like at 0, you see there was no effect in time of MW over M0. At 100, there's also none, but at 1 molar, it's over here. It sprang up like that, just like in the other one. It was very quick. There's only a piece of it, but you can see it goes up. 2 molar, it's following that same very quick aggregation trend. As you go even further, it starts to come down. Time you're at 4 molar, it's down very low, and by 6 mole, it's over. So that follows the window. That's fairly remarkable that the kinetics follow the same thing as the aggregation, the masses associated with the aggregation, the rates are likewise associated. And you can see that the RNAs have their kind of like their own personalities. Some have very fast aggregation over a broader swath of the guanidine. Some have marginal amounts. So you have a big difference in robustness of the mRNA against a powerful denaturant like guanidine hydrochloride. The salt in this bright green just reminds us that it's monotonic. There's no window. Okay, and this is to show the reversibility with the same thing. This is also one of the mRNAs. It's starting at 1 unaggregated, going up. We didn't go past the window. We reversed it before it hit the window, but still you can see it's reversible. Came back down, although not all the way. So we're not sure that might be a dimer, but it is quite reversible. This is a log scale, so it really went up quite high. So the lesson we take from this is that using the salt, all we're doing is screen electrostatic repulsion. So this is the good side of things. When you have net charge, they repel and they don't want to aggregate. That's good. But then there are a number of attractive hydrophobic type of things that can happen. You can have hydrogen bonds. You can have classical hydrophobic effect where you release water and increase its entropy when hydrophobes then get together. You can have pi-pi stacking in these nucleobases. That's actually a quantum mechanical effect. When they approach each other, they induce fluctuating dipoles, which attract each other just like a van der Waals force does. They also have permanent quadrupole moments, which have some attraction in here too. So those are different mechanisms for providing the stickiness, what makes the instability happen. The good guys, electrostatics over here, not to get into a lot of equations. So what we do is then add the energy from the repulsion, that would be the electrostatic, which is a function of ionic strength. The more salt you put in, the weaker and weaker it gets, the more closer they can come to each other. And then you put in the negative energy from whatever hydrophobic interaction is going on, in this case, pi-pi stacking, not the classical hydrophobic effect. See if this is going to come out. No, okay, this, make sure. Okay, so now, like I mentioned, we're looking at aggregation in those first few experiments. But if we do, we subject it to a global stress or temperature once again, we get very interesting behavior. So we hold it in the origin at 44 C. Here we're actually measuring the absolute molecular weight, which you can do. And so it's starting up here, and then it comes down within less than an hour quite a bit, and then it slows way down. And so we did a lot of experiments and determined this is a dissociation. Some of the mRNA is actually in dimers, perhaps even trimers in its equilibrium state. And when you heat it, it actually knocks those apart. But then what's this? When it goes down slowly, that's the well-known autohydrolysis of the mRNA. It's like a backbone biting. And what's really interesting here is this is only 5 hours. So we went to 5 days over here in the acetate buffer with this particular RNA from that table. And you'd see that it doesn't, the hydrolysis never goes all the way down to close to zero, which is, it would go close to zero if you completely chewed up the mRNA by this autohydrolysis. Instead, you get these series of plateaus. And so that was tipping us off to, well, there's lots of types of complex secondary structure in RNA. It's not simple. You get, loops and heatlesses, all kinds of things, and you have different numbers of bases participating in that, which will affect the strength. So it looks like we're hitting different strength plateaus. We're peeling away different amounts of secondary structure as we go up in the temperature. And even all the way up to here, we never got all the way down. So we said, okay, let's try to brute force get rid of the secondary structure by putting it in guanidine, doing the exact same experiment, but in guanidine instead of the acetate. So this here shows the results from 8 different mRNAs from these plateaus here at 44C. So that's right, this one here. And as you can see, of these 8, 3 actually went all the way. So they had weak enough secondary structure that the guanidine took it apart and it went all the way into, they hydrolyzed into fragments, nucleobased fragments. This one here, a little bit. This one here, maybe some. But this one here, I don't believe it really went up. It's probably within error, but it wasn't affected. So you can see several of them were scarcely affected. And so that brings up the idea that some secondary structure is very persistent, and it protects against both aggregation and hydrolysis. So we've linked those two opposite effects, one where you increase the mass by aggregating, the other where you decrease the mass by hydrolysis. So that's an interesting test of robustness for different types of mRNA and sequences. We didn't have the sequences available, as you can imagine. So switching gears now, the last case study I'll show is that of GLP-1 analogs, your Ozempics and Wegovy's and Mounjaro, et cetera. So we did this together with Bachem in Switzerland. And this is pretty amazing, really, what these things are doing. If you take, these are, I didn't write the whole thing out, but they're glucagon-like peptide agonists, and this is the glucagon here without this tail. So that's a natural product produced by our bodies. It's effective in digestive parts of metabolism, but it doesn't last long. It lasts like minutes after it's biosynthesized in the body. But the clever thing is the scientists who did this covalently linked a fatty acid on here so that when they're in solution, they essentially micelize under the classical hydrophobic effect. So those micelides stabilize the glucagon, which otherwise would be gone in minutes, so that it can last days, maybe even longer. Since 18% of the U.S. population is now using these, I guess each person knows, how long it lasts in suppressing hunger. The important thing now for the physics and the stability is that you have surface charges. They go toward the surface, and they separate in space a positive amount and a negative amount. And when you go to the micelle, there's still a certain amount of positive charge and negative, which unless you are at the isoelectric point, there's a net charge. So it's Q2 minus Q1. In our case, Q1, there's more negative charge than positive. But the other important thing is you get the dipole moment. And it really all comes, the dipole moment is the villain here. That's the source of the aggregation, and we can compute the dipole moment over here. Again, I won't go into that part. But when we talked about the model for mRNA, breaking it into the electrostatic and hydrophobic forces competing with each other. Here, what we found after extensive experimentation was that it seems to be controlled purely by electrostatics, not the hydrophobic effect. The hydrophobic effect is responsible for micellization, but not for stability of the micelles. So if we look at R, that's the distance between these. They got a net charge, so this is that nice positive energy. It's repulsive, it keeps them stable. But when they get close enough, this is the whole thing going on. You have that net charge that will attract the dipole, monomole dipole attractive interaction. And of course, van der Waals forces are attractive. That's dipole-dipole. So those create negative energy. This is well here. And if you can get close enough, within a few KT, you can fall into that well and aggregate. So that's the model for the action. And here's an interesting feature. This was for semaglutide. If you dialyze against guanidine on the one hand and then separately against NaCl, there's like almost an order of magnitude between the thresholds of instability. They saturate the system at very definite points. And so why is this threshold for salt so much greater than guanidine? Well, guanidine has a delocalized positive charge, which then interacts with the negative charge on the negative amino acids, and that neutralizes the charge. That brings Q net down. You just lowered Q net, and that's your hero. That's what keeps it stable through the repulsion. And now the evil dipoles come in. You've reduced charge, and the dipoles act much earlier and cause the aggregation to be much lower, guanidine, the aggregation concentration. With that of compared to salt. Okay, and not to dwell on this, but this same model predicts that you can have more than one turning point, which can lead to completely non-monotonic behavior. You can see that this was a liraglutide against guanidine. It actually had a huge narrow initial peak, went back down, and then it has a smaller but broader peak before flattening out, and then reversed out, so it was reversible. And anyway, this all fits within the monopole dipole model. Okay, and then one more test, because usually we think of when you're dealing with proteins and they denature under one of those stresses we talked about, temperature or mechanical stirring. It's the hydrophobic, right? You unfold it and the hydrophobic moieties are exposed in order to, water doesn't like to solubilize those, so the water is shed, vastly increasing the water entropy and pushing the hydrophobic moieties together. And so that's what we see here. We do a temperature scan of a real globular protein, in this case, alpha chymotrypsinogen, and we use the Argand ramp to, it's nice and stable, and then it goes off very, it's not, there is no aggregation temperature, but there is, it depends on your ramp speed, but there is a point at which it goes vastly unstable, which is what we're seeing here. In contrast, the liraglutide and semaglutide don't do that at all. As you heat them up, there is no tertiary structure to unwind and show exposed hydrophobic moieties. Instead, it actually loses a couple monomers from the micelle, and it's completely reversible. It gains them back when you go the other way. So that's more proof that it's not the classical hydrophobic effect driving the GLP behavior. So to put this together into a little chart, we're seeing that the aggregation mechanism for GLP is electrostatic. That's we think we have enough data to show that pretty convincingly. The mRNA was the pi-pi quantum mechanical stacking, and the globular proteins is the classical effect. Let's see if we get this mouse to work. Nope. All right, so it all comes out at once. So just to summarize, we already saw this, but putting it in perspective, you have the pi-pi stacking with mRNA between nucleobases, which makes them pull together and aggregate or associate. They do it reversibly. The globular proteins, you have a native one here, you stress it, it unfolds, that represents the hydrophobic moieties, which then come together, releasing water, and then you get these increasing aggregates. So that's completely classic hydrophobic effect. Whereas with the GLP-1s, we just saw that the existence of a dipole in addition to net charge can lead to the types of instability we monitor. Okay, so to wrap up, the SLS-based technology, we use the Argand for this. It's a great fundamental research tool. You can probe and quantify what happens under these different stressors, whether they be chemical, mechanical, or thermal. As you saw, we can start to tease out the different effects that cause the instability, pi-pi stacking, classical hydrophobicity, anisotropic electrostatic effects. See if mouses. There we go. Okay, and the light scattering is exquisitely sensitive to changes in molar mass. So anything that will change it, like an aggregation or reversible association, a dimerization, or a hydrolysis or other reactions which might bring it down, those are all very, very quickly perceived by the light scattering. Another nice thing about the Argand is that it has multiple cells. And then if you couple it with the dialysis, you can do whole sweeps. And there's no moving parts. So if you look at like a well plate, for example, you can do 96 or more simultaneous samples. You can have a robot or a hapless technician fill those up for you, this 96 wells, put it in a reader, and then it moves around. The plate moves around with respect to the fixed light source and detector. So you can get a lot of different artifacts, whereas in the Argand, everything is fixed, it's stable. So we've been using it with our industrial partners to help accelerate and optimize formulation, get stability that's needed for biologics. The cuvette dialysis, again, that's an adjunct to, we can use with the Argand and other instruments. This ability to sweep through a wide range of concentrations is especially handy. It's one sample, not 96 or more, and you can recover the biologic at the end. A lot of times these biologics are exceedingly precious. I'm sure some of you know, like 1 milligram takes 6 months. And then, as you saw, we could see gradual aggregation or hydrolysis or very sharp thresholds, phase boundaries, and these instability regions. So we're working on these things here at Tulane. If anyone is interested in following up on this, there's this information in a website. So with that, I'd like to thank you all for being present for this, and be happy to take any